In this video, I'm going to show you how the mean of the sampling distribution equals the mean of the population, no matter what the sample size is. Right here I have a small population of 31 people, and each one of these 31 people in this column A have a different value. So let's say that I'm recording the number of hours of TV that each person watches per week. So, for example, person 1 watches 1 hour, person 2 watches 2 hours, and so on. I want to select a sample of 29 people from the population of 31 and calculate the mean of my sample. And this might seem a little bit unrealistic, but I had to use a small population to be able to do this demonstration. So if I'm selecting 29 people out of the 31, and I'm recording the number of hours that each of the 29 selected people watch per week, then each of these columns over here is a different possible sample of 29 people that could be selected. What I had to do to create the possible samples is, well, for the first one, I just left off the first 2 people, and I got a possible sample of 29 people. Over here, I left off this first person. Actually, everything in this demonstration starts at row 2. So here I left off person 1, and I left off person 3. So here I left out 1 and 2. Here I left out 1 and 3. Here I left out 1 and 4. These 3 columns are different possible samples of 29 people. I kept going, and I created all possible samples of 29 people that could be selected from the population of 31 people, meaning I just wrote out all possible combinations of 29 people. Now, what we're going to do is we're going to see what the mean of the population equals, the mean of column A, and we're going to see, then we're going to look at the means of all of these possible samples of 29. So if I type in equals average, and then I highlight the population numbers, I can get the average of the mean of the population. And I didn't do that right. Equals average, highlight, close it off, press enter. The mean of the population is 16. When I added these 31 numbers and divided by 31, the mean came out to 16. I can get the mean of each possible sample of 29 people. What this is going to do for sample 1 is it's going to add the 29 numbers and divide by 21 to get the mean of sample 1. So sample 1 has a mean of 17. If I click here and drag it across, I can get the means of all possible samples of 29 people, because each of these columns is just a different possible sample of 29 people. So we have a lot of different sample means in here. So row 34 is the sampling distribution. All of the numbers in row 34 make up the sampling distribution because they're the means of all possible samples that I could select. If I'm taking a sample of 29 people from the population of 31, and I'm calculating the mean of my 29 selected people, then going across, these are all of the possible samples of 29 people that I could select. Each column is a different possible sample, and here we have the means of all of those possible samples. So row 34 with all of the means of all of the possible samples is the sampling distribution. So, like I said, all the numbers in row 34 make up the sampling distribution. Now, if row 34 is the sampling distribution, then the mean of the sampling distribution would just be the mean of row 34. So I can type in equals average, highlight all the numbers in row 34, the average of row 34, meaning the average of the sampling distribution, is that right there. So it should actually equal the population mean, which means there's something that I didn't do correctly. So it might be that I didn't include all of the rows. So, oh, okay, that's the problem. I have to when I calculated the mean of sample 1 right here, I actually needed to average all numbers starting at row 2, because even though these first 2 rows are blank, when I dragged it across, some of the other possible samples do have numbers in those rows. So I have to include them. So if I want the mean of each possible sample, I do have to include everything starting at row 2. So I'll do it over again. These are actually the means of all the possible samples. And now I'll calculate the mean of the sampling distribution, which is just the mean of row 34. There it is. Close it off. 16.001. It should come out to exactly 16 because the population mean is exactly 16. So I must have made a typo in here somewhere. But you still get the idea. You still get the idea that the mean of the sampling distribution equals the mean of the population, because the population mean was just the mean of these population numbers in column A. So the mean of column A and the mean of row 34 should both be 16. It should come out to the same number. Now, we can also look at a picture to see how the mean of the sampling distribution equals the mean of the population. What I've done now is I've entered the frequencies of all of the values in the population. It's just showing how many times that number has appeared, and it's showing the frequency of each value in the sampling distribution, which is row 34. So if I highlight the population column and all these frequencies, I can make a histogram of the population. Well, it's actually a dot plot, but it's kind of like it shows the same thing as a histogram. So, and it's just going to be flat because in my population, each of the different numbers only appeared once, meaning only one person had each of these different values. In the population that I had, every person had a different number. Um, there was never any number that two people had, so it's just completely flat like this. Every person had their own unique number. But the mean of the population is 16. That's the center of all of these values right here. So the population mean is 16. Now, what about the sampling distribution? I can also make a histogram of the sampling distribution, and the shape won't be totally flat because some of the sample means will appear twice. There are some possible samples that will have the same sample mean. So here's the shape that the sampling distribution has. Here's one sample that has a mean of 16 right here. Over here, this dot right here would be the mean of a sample that has a mean of about 15.7. Out here, this dot would be the mean of a sample that's about 16.8. Here would maybe, right here, would be a sample with a mean of 16. Down here would be another sample with a mean of 16. Because in this column right here, all of these dots are just different possible samples that all have a mean of 16. So the center of the sampling distribution is at 16. So the mean of this sampling distribution equals 16, like we saw. That's why it's centered at 16. And the population over here, the other graph, also had a mean of 16 because its center was at 16. So the mean of the population equals the mean of the sampling distribution. And now we'll see how that's true even with a different sample size. What if instead of taking a sample of 29, I'm taking a sample of 30 out of the 31 people, and I'm asking the 30 selected people, how many hours of TV do you watch per day? And I'm going to calculate the mean of my 30 selected people to estimate the mean of the entire population of 31 people. Well, if I'm taking 30 out of the 31, these columns are all of the possible samples of 30 that I could select. I was able to create the possible samples of 30 by just deleting one certain number from each column. If I delete the first person, that gives me one sample of 30, because it's just 30 out of 31. If I delete person 2, this column D is a different possible sample of 30 people. If I delete this person 3, column E is a third possible sample. So my population hasn't changed. So if I calculate the mean of my population of the individual people, it should still be 16. Um, 15.5. It's a little bit different. I guess it is a little bit of a different population. The numbers have changed. But let's calculate the mean of each possible sample. So I go all the way up to here, close it off. Oh, there aren't as many possible samples because it's a bigger sample size. Let's see what the mean of this sampling distribution equals. The sampling distribution is just this row 33 with all of the means. The mean is 15.5. So if I calculate the mean of all possible samples of 30, and then calculate the mean of all of those sample means, I get 15.5. So the mean of the sampling distribution equals the mean of the population. even with this other sample size of 30. So we've seen this demonstrated with two sample sizes, possible samples of 29 and possible samples of 30.